Good morning, students. And now I'm going to talk about lesson 6.1, which is solving a system of linear equations by graphing. Okay, this may seem new to you since we're just starting chapter 6 right now. Let me go ahead and share my screen. Okay, so first, before we can solve a system of linear equations, you need to know what a system of linear equations is. Okay, I want to remind you, sometimes in mathematics, mathematicians use very complicated sounding words to describe very simple concepts. So a system of linear equations is this: any two or more lines on the same coordinate plane. That's all it means. Okay? See how I have a red line and I have a black line here on a coordinate plane. That is a system. That's all it means. If I had 3 lines or 4 lines or whatever on the coordinate plane, then that would also be a system, but it's a minimum of 2. So if you think of the word system, it basically just means a group of things working together for one goal. And like related words like systemic, which is being used a lot in the news to describe, the racism problem or whatever, it's the idea of different groups or organizations working together, um, either for or against something. So, but again, it's the idea of a system is the whole group of things working together for one. In this case, for math, the system just happens to be 2 or more lines that are sharing the same plane. Okay. Now, um, when you are doing a regular algebra problem, the solution is the answer. Remember, I'd said that early on in summer school. In addition, it's the sum, subtractions, the difference, and so on. But then when you get to algebra, it's called the solution because it can use any operation to get there. Now, when we're talking about graphing, graphing has 2 components to it. One is, of course, the graph itself, but the other is the equation that is used to get the graph. Okay? So the solution to any system would be the points at which the 2 lines cross. Okay? Now, how that works for the graph, it's very simple. What's the solution? The solution is this point because that's the point where the 2 lines cross. Okay, I mean, it can't get any simpler than that. Here's the red line, here's the black line. They both cross. The point at where they cross is the solution. But how does that work with the equation? Okay, because remember, every graph has an equation that represents it. Okay, so on the coordinate plane graph, find the points where the line, the point, not points, where the lines cross. But in the equation, you want to find an ordered pair that makes both equations true. Okay, so in that, let's take a look and see if we can figure this out. So we have a red line here. Let's go ahead and figure out what its solution is. So I'm going to go down to the red line here. Okay. Well, no, I'm sorry, I said solution a minute. Let's figure out what its equation is. So we start with the slope-intercept form. Why again the slope-intercept form? Because it's the one that tells you everything that you need to know. It's the easiest one. Okay. So following along with the slope-intercept form, I'm sorry, I'm just trying to find the best position here. Starting with slope-intercept form, we want to find the slope and the y-intercept. So let's take a look at the red line here and see if we can figure those out. Okay, so I'm going to start with the y-intercept. So my y value, I'm sorry, my x value helps me find the y-intercept. So if I look at my x value, the point where it crosses the y-axis looks to me to be about 1.5 of 1. Okay, so the y-intercept, also known as b, is plus 1.5. Now let's take a look and see if we can find the slope. Start at a point, goes up 1 over 2, up 1 over 2, up 1 over 2. Yep. So the slope would be up 1 over 2. All right, so we were able to get an equation. So y is equal to 1/2 x plus 1.5. Now let's do the same thing with the black line. Okay, first I'm going to start with the y-intercept. Looks like it crosses the y-axis at the point -1. So let's check. I don't go left or right on the x-axis, I go down on the y-axis. So it would be -1. So I'm going to go ahead, instead of writing plus -1, I'll just write -1 as my y-intercept, which is right there. Okay, now from any given point, let's do the slope. 1, 2, 3 up, 1 over. 1, 2, 3 up, 1 over. Okay, so it looks like it's 3 over 1. So I'll just write it as 3. Because remember, anytime you have a fraction over 1, you can just write it as a whole number. So now, by looking at my graph, I was able to ascertain the slope and the y-intercept of both numbers. Okay, so the black line, its equation is y is equal to 3x minus 1, and the red lines is y equals 1/2 x plus 1 and 1/2. Now we can see that the 2 points meet, or the 2 lines meet rather, at this point, and that's what we call the solution. Okay, so what I'm going to do to see if this is correct into the equation, I mean, obviously I can clearly see this is where the point goes because I'm looking at it. But let me see if the point works in the equation. So let me find the point and its ordered pair. So starting with the x, I go over 1 and I go up 2. So its ordered pair would be 1, 2. Okay. All right, so now I'm going to substitute in the numbers 1, 2 for x and y. When you substitute in, it's a good idea to put parentheses. Now the parentheses won't mess up anything else. Oops, I used the wrong color. They won't mess up anything else in your equation. Just the point of using parentheses, make sure that when you substitute in a number that it's going to fit correctly. Like, especially like I have 1/2 here next to 1. If I don't have parentheses, then it doesn't imply times. So that could be mistaken for 1.5 there, but it's 1/2 times 1. Okay, by putting parentheses here, then I can see that it's 3 times 1, not 3 plus 1, or 31. Okay, all right, so let me go ahead and simplify. 3 times 1 is 3. So the question is, does 2 equal 3 minus 1? Yes, it does, because 3 minus 1 is 2, and 2 obviously equals itself. Okay, now, but when I substitute in the point here, then I got a true statement for the black line. Now let's go ahead and do it for the red line. 1/2 times 1 is 1/2. Now I want to remind you that when 1 times anything is just a restatement of that thing. All right, so let's look. 2 is equal to 1/2 plus 1 and 1/2. Yeah, 1 1/2 plus 1/2 is 2. Okay, so in both lines and in both equations, even though my equations are actually different than each other, and I don't mean just different in color, but you can clearly see these are two different equations. They're both written in the same form with different numbers. These the solution of the ordered pair 1, 2, or the point where the lines cross, will actually make both equations true. So it's sort of like a double confirmation. In case your eyes deceive you and say like, oh, well, it looks like it crosses there, but maybe it doesn't. Well, the equations sort of like doubly prove that point. Okay, so finding the solution, to find the solution on the graph, you must find the point where the lines cross, but in the equation, you find the ordered pair that makes both equations true. Okay, now I want to talk about different systems. So for our purposes, there's three different systems that we will be talking about. They are one solution systems, infinite solution systems, and no solution systems. Okay, let me show you how these graph. And they're fairly simple. Again, like I said, with algebra, it's a lot of the complication is just using these big words. Now, a one solution system means that you have two lines that cross at one point. Now, by definition of what we call a line, meaning that it graphs perfectly straight, then it will only have one cross point with another line. The only way that a line could cross something twice, like if my arm represents one line, here's something else, oh, it's going to go back down, cross again, oh, it's going back up. At least one of the lines would have to not be straight. It would have to be curvy. And for mathematic purposes, we would not define that as a line if it's a curve or if it goes up and down or changes direction. So given that two lines by definition are perfectly straight and they cross, then they could only cross at one point because the lines will never curve and come back to cross again at a second point. Okay? So anytime two lines cross, whether they be perpendicular or whether they be diagonal, doesn't matter. They will only cross at one point. So that's a one solution. Now B is what we call an infinite solution. Now this may sound a little bit funny once I explain it, but when lines are together, there are infinite solutions. Now when I mean together, I don't mean that they cross. I mean literally that you have two lines that occupy the same space at the same time. So what I did, for example, is I drew a blue line here, and I drew a red line, and they happen to be on the same space at the same time. So you can clearly see that they connect, and I drew purple in the middle because purple is the mixture of red and blue. Okay, so the idea is this is two lines, but they happen to exist on the same spot. So for example, if I had a point on the red line, then technically that's also a point on the blue line because the blue line crosses the red line. And if I had a point on the blue line, then that would also be on the red line because the red line crosses the blue line. And I drew purple in the middle just as an example, because really this entire space is occupied by two complete lines. The purple line is not a third line, it's actually just the combination of the red and the blue. And I did that on purpose just to illustrate. Okay, so if two lines are on the exact same plane and going the exact same direction, then they actually occupy the same space. And here's my pen. It's kind of like I put another pin on top of it, so they're in the exact same space going the same direction. Moving on, there's a third type, and that is a no solution line. And that one's fairly simple. We talked about it in the last lesson, and that would, or the last two lessons, I think it was 5, 6. The thing is, when you have two lines that are parallel and they're in the same plane, well, obviously if they're parallel, they're in the same plane. But when you have two parallel lines, they are both going the same direction, So, and they're not like the infinite solution line, meaning that every dot that's on one line is also on the other line. Okay. They will never cross. Okay. And remember, I said the idea is like a train track. If the tracks on a train track cross, then the train's going to be in big trouble. Okay. So when the lines are parallel, there are no solutions, meaning that there's no one point on the blue line that is also going to be a point on the red line. Because if you continue to follow them out, they're eventually, I mean, not eventually, they will never cross. They're just going to continue on forever, so they will never have a similar point. Okay, so let me review quickly. One solution, any two lines that cross, the cross point is their solution. Infinite solutions, any two lines that share the exact same space, because remember, a line for our purposes is really an imaginary thought, like the distance from the school to your house is a perfectly straight line. However, I'm sure that there's no exact, like there's no highway directly from your front door to the school. You have to curve and take other roads and get off on streets, stop at lights, make lefts and rights and stuff like that, okay, to get to the school. But a line, basically the distance from the school to your house is one exact distance, okay? Whether that be a mile or 10 miles or 40 miles, doesn't matter, okay? But if it's, let's say it's exactly 40 miles from your front door to the school, it'll probably take you about 45 miles to get there from all of the indirect ways that you go, because you can't take a straight line unless you like fly a missile or something to there. And again, I know I'm talking really strange here, but again, the point I was trying to make is that since lines, for our purposes, are imaginary, they're not a physical thing floating in the air, they just represent a distance, okay? Then since any two lines that share the same space can be exactly in the same spot because they're not actually a physical thing, they're an imaginary thing, okay? I guess one idea that could illustrate that, say here's your friend's house, and here's your apartment building. This one's your apartment, you get the upstairs one, okay? And here is a bird in the sky. Let me move that over so you can see the bird in the sky. Okay, so the idea is the distance from the bird to your apartment is a fixed number. This is my cat. Can you move, baby? Thank you. Oh no, don't come back. Okay, so from the bird to your apartment is a fixed distance, and from the bird to your friend's house is also a fixed distance. Okay, so there's two lines that are in the exact same place and taking the exact same space. Okay, now the blue line, let's just say for just example that would be like 200 feet from the red line, or from your apartment would be, I'm not saying you live in an apartment, you may live in a house, I don't know, I'm just making a story up. But from the red line would be, let's say, about 80 feet. Okay. Now, since both lines occupy the same space, then I'm going to make them purple. Okay. This is Zoe. Say hi, Zoe, to the camera. Of course, my cat doesn't talk. Anyways, so I was just trying to illustrate how you can have two lines taking the same space at the same time. The last one again, there's no solutions if they are parallel, because a solution is defined as a cross point. If there is no cross point, then there is no solution. Now, I want to do some operations here. So the first operation I want to go over is solving by graphing. Okay. Now, if you look at lesson 6.1, and I believe it's on page 382, this is problem 1, so you can look at it if you'd like to. But I have two lines here, y equals x plus 2 and y equals 3x minus 2. Now, I'm going to come up with a table of values. If x is 0, then y would be 2. Because x there is, if that is 0, then it would be 0 times the imaginary 1 is 0, plus 2 is 2. Okay, so if x is 1, 1 plus 2 is 3. If x is 2, 2 plus 2 is 4. If x is 3, then 3 plus 2 is 5. Okay, now let's do the same with the blue line. We'll come up with a table of values. So 3x minus 2. So if x is 0, then we would say 0 times 3 is 0. 0 minus 2 would be negative 2. If x is 1, 1 times 3 is 3, minus 2. 3 minus 2 is 1. If x is 2, 2 times 3 is 6. 6 minus 2 is 4. And if x is 3, 3 times 3 is 9. 9 minus 2 is 7. Okay, now I'm going to plot the red line. Now I will start with my y-intercept, 2. So start at the origin and go up 2 because it's positive 2. 1, 2. Now I can check it with the solution I have. My x value is 0, my y value is 2. So the ordered pair that I had solved for tells me that that's right because I go 0 to the left and 0 to the right. But I do go up 2. So let's plot the rest of the points. 1 over, 1, 2, 3 up. 2 over, 1, 2, 3, 4 up. 3 over, 1, 2, 3, and then 5 up. 1, 2, 3, 4, 5. There, I've got the red line. Now let's plot the blue line. So in the blue line, my y-intercept is minus 2, so that'd be negative 2. So I'm just going to go on the y-axis and just go down 2. And I can compare that 0, negative 2, so that's right. Now, let's do my next points. 1, 1. Start at the origin, go 1 over, 1 up. 2, 4, 1, 2 over, 1, 2, 3, 4 up. Well, look at that. Hey, my lines share a point. Okay, and then we'll do 3, 7 just to finish off. So go over 3, 1, 2, 3, and go up 7. 1, 2, 3, 4, 5, 6, 7. Okay, and now you can see with a straight edge how the lines go. So I'm going to go ahead and connect my points for the red line here. And I'll connect my points for the blue line. And just for fun, I'm going to mark it purple where they meet at because red and blue make purple. Okay, so we could clearly see that the point 2, 4, which happens to be on both tables of values, and also happens to be on our graph, 2, 4 is the solution, okay? So if you were to ask, what is the solution to the system? You would say the solution is the point 2, 4. That would be your answer, okay? So to solve the system by graphing, you pick whatever method you choose to graph. Now remember, if you know that's a linear equation, you only need 2 lines. I made 4 lines, or 4 points. I'm talking wrong. Let me say it again. You only need 2 points to graph a line. However, it is helpful to graph at least 3 or 4 because sometimes between this point and this point, your straight edge here, you might rock it a little bit. It might be off some, okay? So it's kind of good to sort of follow it through. Now in this case, it helped us to follow it through because by graphing, we were able to find the point, okay? Now, if you had looked ahead, you might have noticed that the point did occur twice, okay? All right, so let me just go ahead and do a couple of other problems. This is got it problem number 2, I think we're going to go over. Let me just go ahead and read the problem to you. I'm going to stick it here under the screen. Got it 2 says, one satellite radio service charges $10 per month, plus an activation fee of $20. The second service charges $11 per month, plus an activation fee of $15. In what month was the cost of the service the same? Now, I was just going to recommend to you, if you could pause and then write down this problem. It's also in your book on page 383, so you can also pause and go get your book if you want to. Either way, that would be a great time to do that. Okay, and hopefully you paused, but let's go ahead and I'll continue to help you solve the problem. Okay, so we want to write a system of equations from a word problem. Now, that's not always the easiest to do, so but I want to kind of go over that with you because word problems can be a little bit confusing. Okay, so first we're going to make 2 lines, and then we are going to put them on this coordinate plane that I had made here. So again, color coding is not necessary, but it is helpful, so I'm going to color code my, my lines here just to help make this a little more clear. Okay, so my first line, I'm going to use the formula y is equal to mx plus b to come up with an equation. Now in the problem it said, one service charges $10 per month plus an activation fee of $20. Now the word plus is an indicator that plus something would mean plus b. So that's going to be plus 20. Okay. Now, usually the number that represents the slope, or m, is going to be the number that's multiplied. Okay, so it says one satellite radio service charges $10 per month. Now the word per should clue you in that that's going to be times. So that would be 10. So now we have our formula, our equation. Y is equal to 10x plus 20. Now, what do these represent? So my y value here y is going to it was represented by these numbers, which is going to be the cost. So technically, you could write this as C equals instead of Y. So what does X equal? And then I put these numbers down at the bottom here. X represents the months. Okay, so instead of y equals 10x plus 20, you can say C for cost is equal to 10m plus 20 for months. But I'm going to keep it as x and y just so we don't complicate things. Okay. Now, let's go ahead and figure out the next one. So for the next cable service or satellite service, it says the second service charges $11 per month. So remember, when it says per, that implies times, plus a $15 activation charge. So now we have made our two equations. Y equals 11x plus 15, and y equals 10x plus 20. Okay? So now let's make a table of values for both. Okay. Now, there's really no reason to start with 0 on this one because why start with the 0 month? So I'm going to start with 1. So in the first month would be 1 times 10, so I pay $10 for the service plus $20 for the activation fee. So 10 plus 20 is 30. And I'll just put in parentheses here, C and M for cost and months, just so that you know. But I'm going to continue to call it X and Y just because it's easier to think in terms of the mathematic letters. All right, so let's say in 2 months, okay, 2 times 10 is 20. 20 plus 20 is 40. Okay, I'm going to skip ahead to 4 months. 4 times 10 is 40. And then 40 plus 20 is 60. I'll do 5 months. 5 times 10 is 50. 50 plus 20 is 70. Okay, got some good values there. Now, let's use our blue equation to fill this one out. Okay, so we'll start with the first month. 1 month times $11 fee plus $15 activation. So 15 plus 11 would be 26. Okay. Because 15 plus 10 would be 25. 25 plus 1 would be 26. All right. Now let's try, we'll just try 3. Okay. Again, sometimes you want to skip intervals if you have a very large graph to fill out. Okay. So 3 times 11 is 33. Plus 15 would be 43, 48. Okay. And then we'll do 5. Okay. All right, so 5 times 11 is 55. Plus 15 would be 60, 70. Okay, that looks like enough information for me. Now, let's go ahead and chart this. All right, so looking at my first equation here, I have y is equal to 10x plus 20. So my starting point is plus 20. Okay. Let me put it this way. If I started at 0, then my first point would be 20, because of the one I'm looking for the one that's on the y-axis. Okay, so my next points are 130, so 1 over 30 up. Let's see, 2 and 40, 2 over 40. 40 up. Did I miss an interval here? Because this is looking crooked. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Oh, well, I'm going to go with it. Okay, let's do, we didn't do 3, so let's do 4 and 60. 4 and 60. 5 and 70. Okay, so clearly it looks like I am making a line here other than my first point. Let me see if I can figure out. So that was 0. 0 times 10 plus 20. Not sure why that's coming out wrong, because it looks like the point should actually be right here at 25. I don't know. I must have done something wrong with the first point, because as you can see, it would make a little curve to go to that. But I'm not going to worry about it. If I figure it out, I'll tell you during the meeting. Okay, but anyways, for the rest of it, let's see, where did I put my ruler? Did any of you see where I put my ruler? Aha, found it. Okay. Let me go ahead and match the red points. Looks like I missed it just a little bit there. Okay. Not the best here at making these lines, am I? All right, well, let's go ahead and plot the next one here. Okay, so y is equal to 11x plus 15. So my starting point should be, well, I won't worry about the starting point. I'll just go ahead and plot my points here. So I have 1 and 26. 26 would be a little bit above 25 here. 3 and 48. 3 and 48 would be a little bit below 50. 5 and 70. 5 and 70 would be, again, the exact same point. Okay. So as you can see, the prices for these are very similar. That's a really sloppy job, but as you can see, the lines are very close, but the cross point would be at $70, okay? So that was a problem that was in the book. It's on page 383. Now, the last thing I wanted to show you, and I wrote it, so I should have moved these over here somewhere, but either way, with infinite solutions. So I have two equations here. One of them is written in standard form, and the other one is written in slope-intercept form. So I want to graph them to see what they're going to look like, but I'm not going to graph them. I'm just going to change this one. 2y minus x is equal to 2. I'm going to change it to slope-intercept form. So how do I do that? I have to isolate the y. So I have a 2 next to it and an x. Now remember, in IOB, plus and minus has to be removed for isolation purposes first. So x has been subtracted, so I'm going to add x to both sides. So now I have 2y is equal to, I'm going to write it as x plus 2. Now I switched the order from here just because I have, just because I want to write it in the form of y equals mx plus b. Okay, so that means that my x term must come first. Now, I have to get rid of the 2, so I divide, cancels it out there. I have to divide everything by 2 here. Okay, so 2 over 2 cancels out and becomes 1. Because anytime you have a fraction with the same number on top and the bottom, it's basically saying like 2 divided by 2, which equals 1. Okay? I have x over 2. I want to remind you that the coefficient of x is the invisible 1. So we can actually write that as 1 over 2x. So my red line, when I put it in the slope-intercept form, I have y equals 1/2 x plus 1. Well, if you look at the blue line, y equals 1/2 x plus 1, they are the same. So in this case, I have infinite solutions because my standard form equation and my slope-intercept form equation are the exact same equation. But I had to move them to the same form to tell that, okay? And it's not as easy to graph from a standard form equation. Hope that makes it clear. Thank you very much. Enjoy the video.